So that's one example of freefall. All right, so here's a second example of freefall. Has something like this ever happened to you? Most people will say no, obviously. I had a few students who say yes. They were both of them were females. Evidently, they had the cell phone in their back pockets and they just fell into the toilet. So and one of them ended up having her dad retrieve it for her. The second one actually got the boyfriend. All right, something like this happened to me. It wasn't a cell phone. My keys. I don't know why I was whirling my keys as I was pissing, and next thing you know, I'm pissing on my keys. So what do? What can you do? Take the keys. So just flash a couple of times, grab the keys, and watch them carefully, and don't mention it to anyone, unless of course it's a lecture. All right. So speaking of free fall, the safety harness is designed to work this way. What do you guys think? All right, we got a comment coming up. Okay, no. Okay. If you have an explanation for it, just give me an explanation. One of my students said a number of years ago, and this is what he used to do for a living, evidently, was a window washer for these high rises. He said they would never let you fall this far. Okay, this is like 10, 15 floor drop. It's story drop. That would never happen. Okay, so that's completely wrong. This guy is upside down. Obviously, that's not the way it's supposed to work. This guy ended up bouncing up and down just a little bit. You guys notice that, right? So is this a proper design for something like that? It's almost like a bungee cord, but it's not. You don't want it to be a bungee cord because if you start to go up and down wildly, you may end up hitting the building and end up getting yourself hurt pretty badly. Not to mention it can kill you. So what is a proper design? Would this be a proper design for something like that? We'll figure that out. Get. Where'd you get those? The machine. You want one? No. Here. Take one. I don't want. No, good. I don't want it. Just take one. No, Chris, stop it. Over the balcony, bounce off some respirator thing into the patient. So the motion of the junior mint, is that free fall? What do you guys think? All right, so use the chat option for this one. Okay, is this free fall? Yes or no? Most of you guys will say yes to this one, right? So you will say this is free fall. How about this one? Do you think this is free fall? Yes or no? Now, most of you guys will say, yeah, this is free fall only on the way down, right? How about this one? Do you think this is free fall? Just throwing the ball in the downward direction? And most of you guys will say, no, this is not free fall. Okay, so those of you guys who said this is free fall, you're right. Give yourselves 5 points for that one. Those of you guys who said this is free fall only on the way back down, give yourselves 1 point for that one. Those of you guys who said this is not free fall, don't give yourself any points. Okay, this is free fall, so is this one, so is this one. All right, so when does this become free fall? This becomes free fall as soon as the ball leaves my hand. As soon as the ball leaves my hand, it turns into free fall. That's what it means. So what happens when the ball leaves my hand? Gravity takes over. So free fall is the motion under the influence of gravity and gravity only. So it doesn't matter that the ball is falling or being pushed on or thrown in the downward direction or sideways. As soon as gravity takes over, it becomes free fall. So the definition of free fall is the motion under the influence of gravity and gravity only. So remember the guy inside the elevator? He's on the 10th floor. Cable snaps, he got a broken neck. Okay, so you'll find out, but whatever the theory that you came up with, the beginning of the semester was wrong. Or it wasn't. Some of you guys came pretty close, but it's still wrong.
LA firefighters are
but that's one of the things that we'll get to discover at the end of this.
waiting for backup. The dogs are growing impatient. Watch as they tremble in
Oh my God, the building is on fire.
fear, ready
We got two boxers.
to leap 3 stories to street level. Their chance for survival is slim.
So these dogs are about 30 to 35 feet up. If they have to jump, what are the chances that they will survive? Is it good or is it bad? What do you guys think? What are chances of survival? What are their chances of survival?
It's pretty bad.
You would think so, right? A lot of people think that, hey, dogs are not going to be able to You're not going to be able to survive something like this. This is like jumping from the third floor of a building. What are the chances of survival for a dog? All right, so according to Fox Family, it's pretty slim. Let's change the scenario just a little bit. How about a bear falling backward? Same distance while smoking.
2,200 volts of electricity.
Do you think this is survivable? Yes or no? All right, guys, it's the same distance.
Yes.
All right, all of a sudden you're thinking the dogs are not going to be able to survive this, but the bear may be able to survive this. All right, so do you have an explanation for it?
The bear's unconscious, so at that point his body would just be kind of limp.
Okay, I'm going to give you 5 points for that one. That was a really decent explanation. If the bear is unconscious, what happens to the muscles? They're relaxed, guys. So what does it mean? Which means that the bear's impact time is going to be relatively large. All right, so the relaxed muscles will only increase the impact time. So that may be survivable. That may help bear survive something like this. That's one explanation. You can still come up with 4 more reasons as to why the bear may be able to survive this. So we'll investigate that. So falling objects. Do they fall at a constant speed or do they accelerate? What do you guys think? All right, this is just a simple demonstration. You guys see the ball, right? All right, so while you guys are watching the ball, do you think that the ball is speeding up or do you think it's falling at a constant speed? What do you guys think?
Constant.
Okay, one thing that I'm hearing is some of you guys say constant and some of you guys are thinking it's speeding up. But the reason is because you're not going to be able to tell. Okay, whoever said anything or put anything on the chat, give yourself 2 points so far. Okay, is it speeding up or is it falling at a constant speed? You can't tell by looking at it. Unless you're high on something illegal, then obviously you're going to be hallucinating. You'll probably see some traces, they will change color and whatnot. And then you'll also see some angels or devils or whatever. Demons. All right, but there's enough information here for you to be visual information here for you to be able to conclude something. What is it? There's something that happens that tells you that this is either speeding up or it's falling at a constant speed. So the question is what? Which one? All right, here, say it again.
Gravity.
Forget gravity. All right, guys, is it speeding up or is it falling at a constant speed? Okay, notice that it goes from 0 to something else. Do you guys see that? It goes from 0 to something else. So which means that it's accelerating, right? If it didn't go from 0 to something else, you wouldn't need a parachute when you jump from an airplane. You would be stuck up there unless someone came to your rescue. You would starve to death. Do you get it? So falling objects do accelerate. Where's the evidence? Well, they go from 0 to something else. Okay, now when I throw the ball back up against gravity, do you guys notice that it slows down? It slows down to a stop. So that's also acceleration. So the falling objects do accelerate. How do we know? When drop will go from 0 to something else. And also, we know that throwing up against gravity, it will slow down to a stop. So the falling objects do accelerate. An experimental verification of it, when dropped, they will go from 0 to something else. And thrown up against gravity, it will slow down to a stop. All right, that's it. Okay. Got the best answer? Place it in the chat. Okay, very good. C. Okay, so falling objects will speed up, right? So speed is going to go up, direction is the same, so the velocity is going to increase. So C is the best answer. Give yourself 5 points for that one. All right, so the next question is, the falling objects, do they fall at a constant rate of acceleration, or does the rate of acceleration vary depending upon the weight? This requires a bit of a demonstration one more time. All right, so does the rate vary depending upon the weight? Okay, let's do a simple experiment. Does you guys see the piece of paper and the ball? Now, remember, guys, this ball is like 1,000 times heavier than this piece of paper, so when I drop it, which one is going to land first? Well, you know the answer, so let's just do the experiment demonstration. All right, notice that the ball ends up falling much faster, right? All right, so the question is why? Why is it that the ball is actually falling faster than a piece of paper? Now, you can come up with 2 answers for it. So what are those reasons?
Air resistance.
All right, give yourself 5 points. The air resistance may be a factor. The other is...
Even if the drag was the same, the ball has a higher mass, so the air resistance won't have as dramatic an effect.
So I'll give you 5 points for that one. Air resistance is a factor. Also, the weight is a factor in this case, right? All right. So the question is, which one is a factor? Okay. So I got 2 pieces of paper, same size, same shape. They weigh the same. If weight is a determining factor in terms of how fast an object is going to fall, then because they weigh the same, they should fall at the same rate. Right? That's what it means. So if I were to grab one of the papers and just crumple it, I'm not changing its weight. It still weighs the same. So weight is a determining factor. When I drop them from the same height, they should still accelerate at the same rate. But when you do the experiment, immediately you notice that air friction is a factor, so it's undeniable. All right, so the crumpled paper ends up falling much faster. So the question is, what happens if the effects of air friction becomes negligible? Does weight a factor under the circumstances? Guys, crumpled paper, and you got the ball. Remember, this ball is still 1,000 times, more than 1,000 times heavier than this piece of paper. And also, I want you to remember that this piece of paper, because it's crumpled up, it doesn't experience a lot of air friction. It doesn't experience a lot of drag. So do you think this piece of paper is going to fall at the same rate as a ball, which is about 1,000 times heavier? Okay, this is the demonstration. All right, I'm going to drop them, and they will just disappear from your view within 0.4 of a second, guys. So don't blink. Okay, so this is the experiment. I'm just going to drop them from here, and you guys were able to see a blur. Within the blur, what do you guys see? Within the blur, you notice what happens. They're falling at the same rate. Isn't that weird? All right, so when the effects of air friction becomes negligible or ignorable, the weight doesn't matter, does it? When gravity is the only force acting, weight does not matter. That's what it is. So that's known as free fall. So all objects will fall at the same rate of acceleration when the effects of air friction is negligible or ignorable. I mean, if we were to do the experiment at the surface of the moon, this piece of paper, and this ball would still be falling at the same rate. In fact, we did the experiment at the surface of the moon. One of the last visits to the moon.
Explored the airless surface of the moon. He couldn't resist repeating this classic experiment for all the world to see.
Well, in my left hand, I have a feather. In my right hand, a hammer. I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? But I'm not admitting that Mr. Galileo was correct in his findings.
All right, guys, except the difference between what I did and what they did is that cost us like $1 billion. It's the same experiment. Galileo is the guy who came up with that, believe it or not, 400 years ago. He's the father of science. He's this guy who said, hey, if you got a theory, make sure that the theory makes predictions so we can test those predictions. It was in his 70s, under a house arrest, life was boring, and that's when he decided to conduct these experiments, physics experiments that we know him by, basically. So he's the one, he said, hey, only in a vacuum, in an airless environment, or when the air friction is negligible, all objects, regardless of their weights, will fall at the same rate. How's that? Now, the rate at which the object accelerates is known as g. All right, so this is the acceleration due to gravity. And notice that it's 10 meters per second squared. Remember, we were expressing accelerations in terms of your own body weight. All right, that's where the term comes from. All right, so 1g is going to feel like your own body weight, in essence. It's roughly about 10 meters per second squared. The actual number is 9.8 or 9.81, depending upon which book you use or where you do the experiment. It may vary just slightly. All right, so the weight doesn't matter, which means that both objects will hit the ground at the same time. So it sees the best answer, give yourself 5 points for that one. All right, so for relatively heavy objects, for relatively short distances, air friction is negligible. All right, so when we go back to slow motion, all right, so the ball is here, his center of mass is located there. Notice that there's relative position remains constant. So for relatively short distances, for relatively heavy objects, friction usually is negligible or can be negligible. Okay, so let's do a mathematical modeling here. So far, we talked about uniform motion, uniformly accelerated motion, which means that the acceleration is constant. It's going to be speeding up in this direction within this distance and within that time period. All right, so we were able to describe this motion using 3 equations. Okay, real fast, guys. What's the meaning of the first equation? I'll give you 5 points for that one. What does the first equation tell us? All right, so race, I need more than that. I'll give you 2 points for that one. Okay, first equation is going to locate object for you at a given point in time, right? So if you know the time, you know exactly where the object is. Okay, Juan, give yourself 5 points. Jessica, likewise. Okay, so if you know the time, you know where the object is, right? What does the second equation represent?
How fast it's moving at the given time.
Yeah, give yourself 5 points. It's how fast it's moving at a given point in time. So if you know the time, you know how fast it's moving. What's the meaning of the third equation?
Speed at that location in time.
Speed at that location. Give yourself 5 points. Very good. All right. So you guys are actually putting stuff on the chat once again. Give yourself 5 points. All right. So immediately, the location becomes predictable for a given time. Speed becomes predictable at that time as well as at the location. That's it. Okay. So what do we know? In free fall, we know that the acceleration is going to be constant, right? It's the same as uniform acceleration. This time it's along the y direction. So this thing is going to follow a certain distance within that time period while accelerating in the downward direction. So what we'll do is we'll just modify the equations. All right, so we'll use the same 3 equations, except the letter x is going to turn into letter y. It's going to turn into g. And the initial and final velocities will be initial and final velocities along the x and the y directions. That's it. So we'll just modify the formulas. We'll take the same formulas and just modify them just a little bit. All right, notice that this is y modified from x to y. And once again, this gets modified using the transformations from there. And that's it. So in essence, these formulas are identical to those formulas. So now these become the free fall formulas. That's it. All right, so give me the interpretation of the first one. I'll give you guys 5 points one more time. So, all right, so what's the meaning of the first formula? Okay, very good. If you know the time, you know the position, right? If you know the time, you know how far the object is falling. If you know the time, you know the vertical position of the object. You know the time, you know how far the object is falling up to that point. Okay, what's the meaning of the next formula? Okay, very good. Connor says, you know how fast it's falling at that point, right? You know the vertical speed at that time. Very good. So you know the vertical position at this point, you know how far the object is falling, and you also know how fast the object is falling at that point, right? So what's the meaning of the last one? Okay, very good. Vertical velocity at a position. So if you know the position, you know how fast it's moving at that position, right? So the first formula is going to tell you how far the object is going to fall within this time period. It's going to tell you how fast it's going to be moving at that time and at that location. So that's it. Once again, the motion itself is 100% predictable.
Did you know that a car hitting a wall at 40 miles per hour hits with the same force as if it fell off a 5-story building? It's not easy getting through the teenagers today. So at Liberty Mutual, we produce a video especially for teens about car safety because we'll do whatever it takes to keep them safe on the road. Liberty Mutual, it's more than insurance. It's insurance in action. Now for 60 miles per hour. Look at that.
Okay, guys, given the fact that this is a commercial, what are the chances that the physics is accurate? The reason why I'm asking that question is a lot of the times on commercial TV, the science is not very accurate. It's getting better. On the Science Channel, they're doing a much better job. If you really want to get some good science, just go to Nova. Public TV does the best job. BBC is amazing. Okay, commercial TV, not so much. So, given the fact that the commercial, so what are the chances that
the science is good? Did you know that a car hitting a wall at 40 miles per hour hits with the same force as if it fell off a 5-story building? The car hitting a wall at 40 miles per hour hits with the same force as if it fell off a 5-story building. The car hitting.
All right, so that's the statement that we will check. We will try to verify. So, a car falling from the 5-story building is going to hit the ground, or will it, at 40 miles per hour. That's what it is. So this is problem number 17, which requires a bit of a verification. So she claims that the car falling from a 5-story building is going to hit the ground at 40 miles per hour. So let's check to see if it's true, right? A 5-story building is roughly about 50 feet, so that's what we're going to use. So let's figure out the impact speed of this object. So the initial speed is going to be 0. Distance falling is going to be 50 feet. G roughly about 10. Figure out the speed and then express it in terms of miles per hour. Right, so we listed everything. Now we need to do convergence. In terms of convergence, speed needs to be expressed in terms of meters. So we did a conversion by multiplying it by a conversion factor. So that's the number that we got. So the next step is which formula to pick. All right, boom, boom, boom. So just look at the symbols, pick the best formula based upon the symbols. Notice that the only one that you can use, it just vanished to the side because Zoom ended up changing their parameters. So it was not supposed to record people on the side, but it did. Okay. Which means that you have to use the third formula for that one. Okay, now you can see it. All right, so these symbols, the third formula. All right, so if you have any zeros, plug in the zeros. The initial speed is 0, so this term is going to drop. If you have the square, by taking the square root of both sides. There's plus and minus, just assume that it's plus for the time being. All right, so now plug the numbers in. It's going to be roughly about 10. So we end up getting a number, and in terms of meters per second, converted to miles per hour, it's going to be 39 miles per hour, right? So what does it mean? It's pretty close to 40, approximately. Not bad. Commercial is fairly accurate in that sense. Okay, I'm actually impressed. Okay, now let's go back. Having worked at an art school, commercial art school, for roughly about 20 years, I can tell you that there's a lot wrong with this commercial. Just because you get the numbers right doesn't mean that it's accurate. All right, art students had to submit projects. 10% of their final grades came from these creative projects. And then you got to remember, I had these film students who are working as directors today. 1 or 2 of them are working for Disney, for example. There are a lot of commercial art students in terms of game arts and all that stuff. So they needed physics for that sort of stuff. Okay. Now, the evaluation of a project like this will go like following. Number 1, she looks like she could be a high school physics teacher. So acting is phenomenal. I'm looking at the students' complete apathy. That's normal because it's physics.
40 miles per hour.
This guy is carefully selected. Look at the face. You can tell that he's high on something legal or illegal. He's not really connected to what's going on. And then something weird happens. The representation of reality starts to fail. It starts to go to hell, in essence. She is pushing a car off the building backward. Is this the way it would be done? Absolutely not. I can see that she can push her car easily. Look at the leg. She's very strong. The problem with the way she's pushing the car is it's backwards. If the car goes off the building, she can also potentially go off the building.
It's not easy getting.
Then it starts to get worse. If you can somehow push a car off a building like that, it's not going to go down straight down like that. It's going to start to it's going to start to rotate slowly. All right, so the rotation is missing. And then it still gets worse. Notice that there was a flash of light just before impact. It should never happen. And then there's a flash of light again. Special effects artists completely got it wrong. At 40 miles per hour, there's not supposed to be a flash unless something is terribly wrong with the car. And there were 2 flashes of light.
Liberty Mutual, we produce a video, especially for teens, about car safety, because we'll do whatever it takes.
All right, so this was the only drop that they had.
Keep them safe on the road. Liberty Mutual.
Using our crane, and that's it.
Now for 50 miles per hour.
So the numbers are accurate. Representation of reality, the real physics is lacking. That would be a C project. Artistically, it's really well done. There's always 4 seconds.
Did you know that
Changing scene, the angles are changing.
40 miles
Artistically, it's well done. All right, this would be more like a D project overall. All right, so that's what happens when I'm watching movies. You see all these details, and after a while, it gets to be distracting. Okay, very good. Neglecting the effects of air friction, everything is going to follow at the same rate. One drop, everything is going to be falling at the same speed. So he's the best answer you can give us 5 points for that one. All right, so you drop a ball, throw a ball in the downward direction, and you throw a ball in the upward direction. All right, so which ball is going to have the greatest acceleration? If you throw a ball in the upward direction and the downward direction with identical speeds, which one is going to have the largest impact speed? What's the acceleration of the ball when it reaches its peak point in motion? What's the acceleration of the ball while you're throwing it? Okay, let's do quick demonstrations for these ones. Okay. All right, guys, which ball has the larger acceleration, this one or this one? Okay, all right, just hold on to your answers. You will get to self-evaluate. If you're right, you will get to add 5 points to your participation. And obviously, if you're wrong, nothing. Okay, so which one is the larger acceleration, this one or this one? This one or this one? I drop the ball, I throw the ball in the downward direction. I drop the ball, I throw the ball in the downward direction. So which one is the larger acceleration? So that's one of the questions. The next one is, I'm going to throw the ball in the downward direction and in the upward direction with identical speeds. If this is 20 miles per hour, this is 20 miles per hour. Okay, so up 20 miles per hour, down 20 miles per hour. So which ball is going to hit the ground at a larger speed? Which one is going to have a larger impact speed? Which one is going to have a larger free fall speed? That's what it means. The third question is, notice that when I throw the ball up, it comes to a stop at some point. So it's going to go up, it stops. At the moment the ball stops, what's the acceleration? It's either 0 or it's not. Those are the decisions. And also, while I'm throwing the ball, while I'm still in contact with the ball, what is the acceleration of that ball? Is it bigger, the same, or smaller than the gravitational acceleration? So those are the questions we will try to answer. Okay, so remember what it is that you guys are thinking, and then you will have to evaluate yourselves based on that. Okay, so I drop a ball, and so I'm going to follow the ball for 3 seconds. And notice that the ball is going to be speeding up in that direction. That's the reason why the distance is increasing per second time interval. And gravity is the only force acting, and gravity makes things speed up at a rate of 10 meters per second each and every single second. So acceleration due to gravity is going to be 10 meters per second squared. What that means is this ball is going to go when dropped from 0 to 10 within the first second, and 10 to 20 within the next second. That's it. All right, so acceleration is going to be, when you go from 0 to 10 in a single second, it's going to be 10. When you go from 10 to 20 in the next second, it's still going to be 10. So when the ball is dropped, the acceleration of the ball is going to be 10 meters per second each and every single second. So which means that it's going to keep gaining speed at a rate of 10 meters per second each and every single second. So next case is what would happen if you were to throw the ball in the downward direction, right? So that's what we're going to be looking at. So I'll throw the ball in the downward direction. That's 20 meters per second, guys. That's like 45 miles per hour. All right, so you just chuck the ball in the downward direction at 45 miles per hour. So that's 20 meters per second. So what happens, as soon as the ball leaves your hand, gravity takes over, right? So what will the gravity do? Gravity says here, I'm going to make you go faster at a rate of 10 meters per second each and every single second. What that means is within the next second, this ball is going to be moving at 30 meters per second. Got it? It's going to be moving at 30 meters per second. So you drop it, it goes from 0 to 10, acceleration is 10. When you throw it, it goes from 20 to 30, acceleration is still 10. All right, this one is falling faster, but this one is not falling as fast. They're still accelerating at the same rate. So what's the difference between this and that? No initial speed here. There's an initial speed there. So the difference between this and that is this doesn't have an initial speed, this does. Once the ball leaves my hand, it's always going to speed up at a constant rate. That's what it means. So which one is a larger acceleration? This one or this one? Both of them are the same. All right, so that question is set up. Now let's move on to the next one. All right, case number 1 is done. Move on to case number 2. This time, what I'm going to do is I'm going to throw a ball in the upward direction and in the downward direction with identical speeds. Okay, let's throw this ball in the downward direction and follow for 1 single second. So it's going to, and then I will place the ground right there. So it's going to, gravity is going to take over. So which means that this ball is going to go from 20 to 30 within the next second. And then I will throw this ball in the upward direction. Guys, acceleration has direction, right? The gravitational acceleration is in the downward direction. So if you go up against gravity, you will slow down at this constant rate. If you're moving in the direction of gravity, you will speed up at this constant rate. That's what it means. So thrown up against gravity, you will slow down. So within 1 single second, we'll go from 20 to 10. Within the next second, you will go from 10 to 0. What goes up must come down. So within the next second, we'll come down at 10 meters per second. Next second is going to be 20. Let it drop 1 more second. It's going to be 30 meters per second. This is 30, so is this one. All right, only difference between this motion on this side and that motion is this takes 1 second. This is going to take 1, 2, 3, 4, 5 seconds. The end result is going to be the same. All right, so both balls are going to have the same speed, same impact speed, same final free fall speed. All right, so the next question is, okay, move forward. Notice that the ball comes to a stop at this point, right? So the question is, in fact, the ball is not moving at this point. Does it have an acceleration? Most of you guys will say no. If you say no, you're missing the point. Acceleration means change in velocity, guys. All right, is the ball moving before it stops? If the answer is yes, it's accelerating. Is it moving right after it stops? The answer is yes, it's still accelerating. It's not like a bus stop. You don't come to a stop and stay there. It's part of motion. It goes up and comes back down. All right, it doesn't stay there. If it's moving before or after, it's always accelerating. In fact, about a second before it stops, it's going at 10 meters per second, so it goes from 10 to 0. So the acceleration is 10. And then it goes from 0 to 10, so the acceleration is still 10. All right? In fact, once the ball leaves your hand, the acceleration remains constant. It's going to be g. It's going to be 10, roughly about 10 meters per second squared. Why? Because that's when the gravity takes over. All right. You kind of knew the answer because I gave you the answer in the beginning of the lecture. Now you understand it because the understanding was missing. All right. Once the ball leaves your hand, the acceleration is going to be constant. Gravity takes over, and if you're going up against gravity, you will slow down at a constant rate. If you're moving in the direction of gravity, you will speed up at a constant rate. All right, so which one is not an example of free fall? The one which is not an example of free fall is the person actually being in control of the ball, right? If the person is in contact with the ball while the ball is in the process of being thrown, that's not free fall. Which means that the acceleration could be larger than 10, smaller than 10. It could be the same as 10, but that's not gravity. So that's not motion under the influence of gravity. So those of you guys who put D, give yourselves 5 points for that one. So at the peak of its trajectory, when you throw a ball in the opposite direction, right there, it's not moving. So the velocity at that point is going to be 0. That's 5 points for that one. Okay, so let's transition from free fall to impact.
If it wasn't scary, it would be worth doing.
All right. Oh, God. Here
Yeah,
we go.
look out there. Right out there.
All right, so bungee jumping. All right, she changed her mind, but her body was committed. She changed her mind because she got scared. Despite the fact that this is perfectly safe. What makes it safe, guys? What makes it safe is the fact that the bungee cord is going to stretch, increasing the acceleration time. So which means that it's going to be able to reduce the acceleration and make it survivable. Not only will it make it survivable, but also will make it fun. That's what it does. All right. So what happens is free fall goes into some kind of acceleration. All right. So large enough impact time is going to reduce the acceleration. It's going to make it survivable.
You still think
Or free fall can come with impact.
it was a good idea?
I think I should be good, but I don't. You know, it's doable jump. It really is. I have no reservations other than my own fear.
Dude, make a reservation. It was a good idea.
Something like this.
I think I should be good, but
Are you thinking to yourself, hey, this guy is trying to test to see if this is a doable jump? Guys, when you see someone jumping from a bridge, obviously you're thinking it's a suicide, right?
it's doable jump.
This is a doable jump, and then this guy jumps. As far as he's concerned, it's a doable jump. Is that a doable jump? I got news for you guys. Every single jump is doable. Only thing you have to do is jump. The question is that survivable? All right, so let's investigate. So I timed this. It's a 5-second drop. If this is a 5-second drop, how fast do you think you might be going at the time you hit the water? All right, so it's a 5-second drop. Okay, so just let's ignore the effects of air friction. Air friction is going to be somewhat negligible in that distance. And then figure out the speed in terms of miles per hour. All right, so find these symbols. Which formula? The only one that you can use is the second one. All right, everything is expressed in terms of the metric units. The initial speed is going to be 0. And that's the final answer. So G is roughly about 10, so you got 5, so it should give you 50 meters per second. The miles per hour is going to be 112 miles per hour. So That guy hit water at 112 miles per hour. So 112 miles per hour, is that survivable? Okay, now let's have a quick discussion. Guys, when you hit water at that speed, what does it feel like? It feels like concrete, right? All right, so it's like, if water is going to feel like concrete, can you actually survive the impact? Is that survivable? Yes or no? What do you guys think? All right, how about getting hit by a train at 112 miles per hour? Is that survivable? What do you think? Speaking of concrete, train is like concrete, right? No. So hitting water at 112, is that survivable? People will say no because it feels like you're hitting concrete. It's almost like getting hit by a train at 112 miles per hour. Is that survivable? No, 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 it's not survivable. That's what people say. Guys, there's a difference though. You got to remember, water gives. Train won't give. Water gives. When was the last time you felt so thirsty that you decided to drink a train down? How well did that go down? All right, you can hit water just like that and try to do the same thing in front of an incoming train. Check to see if that's going to make that much of a difference. When you hit water, if it feels like concrete, which means that the pain registers, which means that there's a large enough impact time for you to actually feel the pain. Getting hit by a train is not going to have any pain because it's not going to register. It happens so fast. All right, it takes about 1/10 of a second for the pain to register. So let's use that 1/10 of a second. And let's do an impact analysis. All right, so there's 112 miles per hour. So you're going to hit water at 112 miles per hour. All right, so you're coming down. You're hitting water at 50 meters per second. All right, so your final free fall speed is going to become your initial impact speed. Okay, within 1/10 of a second, that's how long it takes for the pain to register. You will come to a stop. All right, so what would be the acceleration if that's the case? And now let's check to see if it's survivable. All right, so we do an impact analysis. You will go through jerking motion, which means that we have to use the average acceleration. You know the final speed is going to be 0. Okay, guys, this is your estimated impact time. So I'm just going to change the notation so we don't confuse this one with that one. Okay. All right, so this is your estimated impact time. This is your free fall time. All right, and so estimated impact time is going to be 1/10 of a second. So it's going to give you 50 Gs. 50 Gs for a fraction of a second. Is that survivable? Okay, so we got a bunch of numbers. We did learn up to this point. What do we know? You can survive between 7 to 12 up to a few minutes. All right, so that's a finding. You can survive between 20 to 25 Gs up to a few seconds, and for a fraction of a second, you can survive up to 140 Gs under extreme constraints. So what does it mean? Is this survivable? It can be survivable. Remember, this is still large enough to break your bones. Potentially, you can break your neck and die from it. Aside from that, you can't survive, but you will have broken bones. All right, so because you're over 25 Gs, this will be survivable, which means the initial impact is going to be survivable. That's what it means. All right, so check to see what happened.
When he's unconscious.
Yeah, it looked like something had gone terribly wrong. He continued to be unconscious. And I tried to pull him up out of the water. He roughly weighs about 200 pounds. And he had this look in his face like, what have I done? What have I done? What have I done? I was unconscious under the water, lying face down in the water, and even pulling me out of the water. I do not remember anything until I was well into the boat on my way back. If you ever do that again? After the jump, I went home and slept until the following day. And when I woke up, I realized I was in pain. I went down to the hospital, and I was there for quite some time, and took the x-rays, and found out that I had a concussion fracture in my spine, that I had bruised ribs, and other than that, I was in pretty good shape.
That'll sound like our definition of pretty good shape.
I needed 5 weeks rehabilitation with my back.
He still thinks it was a good idea.
Everybody thinks I should regret it, but I don't. You know, everybody says it was foolish. It's a doable jump. It really is. I have no reservations other than my own fear.
Dude, make a reservation on the Born to Lose plane.
All right, guys, here's something weird here. Notice that he turns his body. I don't know if it's intentional or if he did it reflexively. And then he ends up hitting the water with his back first. Okay, and what happened was I ended up reducing his impact on. And that made it worse. It was 50 Gs, so he fractured his back.
Once you get up there,
this guy on the other hand, once again, this is a weird looking thing. You're thinking this guy's
on fire. There's no turning back.
He sets himself on fire first.
Douses himself with kerosene and then lights him.
And then he's gonna.
Luckily, he's not burning for long.
Once I hit that water.
And then he jumps. It looks once again. It looks weird. It looks like a suicide attempt. It's roughly the same distance. So this guy's also gonna hit the water over 100 miles per hour.
Life at risk to spare.
Except the difference between this guy and the other guy. This guy is a professional diver. All right, this is an event he's trying to raise money for cancer research or something, and he's trying to make it interesting for himself by setting himself on fire. All right, so the difference between the first guy and the second guy is this guy actually knows how to hit the water. All right, feet down first, head down first. He's got to increase the impact time. This guy's impact time is about a second long. That's about 4 to 5 Gs, so that's nothing. All right, worst case scenario, the other guy's 50 Gs. That was survivable. He had a broken. He ended up fracturing his back. A lot of people jump in suicides. Obviously, they jump from bridges. Believe it or not, most of them survive the initial impact. The problem is 50 Gs, you've got broken bones. go in and out of consciousness. Sometimes the lungs are collapsed. They got broken legs, broken arms. They're not able to swim. If no one sees you fall, no one comes to your rescue. So that's what the problem is. Initial impact is usually survival. So water gives.
It used to be a sort of game where blindfolded men try to find these women in the pool, and from what we can tell, the guy on the left is no good at it.
Water gives regardless of from what distance you're jumping from. The problem is the concrete doesn't give. Notice that you also bounce when you hit concrete. Okay, you will get your impact time from your body. So which means that something has to happen to your body. All right, and usually if you're going too fast, you're gonna have broken bones, this and that. All right, so from that distance, which is if it's a 5-second drop onto concrete, that's acceleration is gonna be about 5,000 Gs. That would be their point impact. There's no surviving that.
Shooters go off to work. Now they're sitting ducks with an uncertain fate. LA firefighters are waiting for backup. The dogs are growing impatient.
Right,
watch as they triple in. The first dog is hurried down a ladder to safety. While on the ladder, the second dog leaps from the rooftop. Incredibly, he lands in one piece.
Okay, so just because it's 30 feet up doesn't mean that it's an automatic death sentence, right? Okay, the dog was able to survive, so the question is why? Evidently, the dog experienced a favorable impact time. How is that possible? All right, landing on grass, obviously it's going to increase the impact time. If the dog was caught by someone, that's going to increase the impact time. You can still break bones and be able to survive something like that. All right, so those were reasons why the dog was able to do well.
Albuquerque, New Mexico. A panicked bear wanders out of the mountains and into town in search of her lost cub. As she runs through residential neighborhoods, people hide indoors, fearful of being attacked. Animal control officers armed with tranquilizer guns corner the bear, and she races up utility poles to avoid capture.
Just like any wild animal, if it perceives danger, it perceives that it's going to be threatened or hurt, it will attack.
But it's not the people who are at risk, it's the bear. She's sitting dangerously close to high-voltage power lines. One wrong move and she'll be electrocuted. She searches frantically for her cub, unaware that it's already been found and is being protected by the animal control officers. The mother bear is confused and disoriented.
It was just going nuts. It was in the true panic.
The game warden fires a tranquilizer dart to subdue the animal, but it doesn't take effect.
But this particular bear, we feel, was so stressed, so panicked, that those drugs were taking a long time to work.
After nearly an hour, the bear becomes drowsy. It's a heart-wrenching sight as she struggles to keep her balance. Suddenly, the bear loses her grip. She's jolted with 7,200 volts of electricity and falls to the ground. Animal control officers run to her, but they're afraid they'll be too late.
That was it. The bear was dead. We really thought that bear was dead.
But miraculously, she is still breathing. Rescuers rush the animal to a veterinary hospital, determined to save her life and reunite her with her cub.
Since that bear was still alive, and bears are really tough animals, that there was a chance that this bear could make it.
A team of specialists administers emergency care to save the animal's life. After weeks of nurturing at a nearby zoo, she makes a full recovery. She's released back into the wild with her cub at her side, and an appropriate new nickname, Sparky.
Okay, so I need 5 reasons as to how the bear survived the impact. Okay, so we came up with one reason. So the bear was unconscious, right? So that increases the impact time. What else? What else do you think might increase the impact time? Go once, go twice, yell out, say something. Okay, grass, absolutely. Give yourself 5 points. Grass is going to increase the impact time. What else?
Thickness of fur.
Fur, yeah. Fur's gonna. The bear's got thick fur. Give yourself 5 points. Fur is going to help. What else? Ignore the transformer. I'll give you 2 points. No, I'm talking about just let's focus on the impact, surviving impact.
Stronger body.
Okay, I'll give you 2 points on that one. I don't care about that. What else? Stronger body is not going to make that much of a difference. Okay, what else? All right, so we got the fur. The bear is unconscious. Landing on grass. The way the bear landed, so flat against the surface, is going to increase. It's going to disperse the impact force. Lastly, the fat. Damn it, the fat. Fat helps. It's like your natural crumple zone. It's like an airbags. All right, so that's certainly going to help. What doesn't help
Put a child in a shopping cart at the store, and you probably,
regardless of the distances, you don't want to hit concrete.
Realize that you may have been putting your child in real danger, though you might change your mind after what you're about to see. Arnold Diaz is going to show us how thousands of children are seriously injured in shopping cart accidents, sometimes even when they're wearing a seatbelt. Take a look at this.
It may not seem risky to put your child in a shopping cart, but the fact is there's been a dramatic increase in the reported number of children injured in shopping cart accidents. And it can happen in ways you might not expect.
So hitting concrete is no good. Notice that the concrete doesn't give, which means that your body has to give. You have to get your impact time from somewhere.
And John Moore,
Shopping cart and put my
handle. It can create a potential.
You're getting ready to talk to your child. You're putting your weight down. And boom. Just like that. And he comes down on his head.
He comes down on his head, or he comes down and breaks a leg. Her parents say that's exactly what happened to Jessica Borzaleka in another company's cart when she was 4.
So you have to get the impact time from your body in the worst case scenario. and then your bones will start to act like your crumple zone. All right, most bones will start to break and fracture around 25 Gs. Inertia increases the impact time, guys. It's almost by design. I don't want to say design, but it's survival of the fittest. So your bones will have to break, or else you will suffer massive internal bleeding. All right, so the bones will break in order to increase your impact time. It increases about up to almost 10th of a second. Concrete doesn't give, so you have to get the impact time from your body. All right, so it's the Darwin Awards. This guy, who happens to be a Canadian attorney living in Toronto, decided to demonstrate the strength of the windows in his office building to his client. I don't know for what purpose. So he runs to the window and puts his shoulder, and window gives. He plunges to his death. 24 floors, guys. That's like 250 feet. That was dead upon impact. Regardless of your nationality, whether or not you have free healthcare, it's not survivable. Hitting concrete from that distance, you won't be able to survive. Concrete doesn't get. All right, how about a cat? The cats are said to have 9 lives. Do you think that the cat would do better than a human being from that distance? What do you guys think?
Yes.
What do you mean, yes? Arun, I love your confidence. You're like, yeah, yes, the cat's would be fun. No. In fact, if you're going to go up 24 floors, 25 floors, we might as well make it interesting, right? I mean, we live in Chicago, near Chicago. We got one of the tallest buildings in the world. Right? Sears Tower, formerly known as the Sears Tower. Willis Tower, Big Willie, whatever. I want to just take a cat. What would happen if we were to take the cat to the top of the Sears Tower and just drop the cat? You think that the cat is going to be fine? In case you don't know, all the way to the top floor is getting 1,450 feet tall. That's what it is. Now, I imagine that, I don't know how I'm going to do it. I smuggle a cat onto the top of the Sears Tower. And then let me just drop the cat from the top. All right, and here's the bird eye perspective of what's happening. What do you think is going to happen to the cat? Splat? Oh, my dog got excited.
It's going to go splat.
It's going to go splat. That's what most people will say. By the way, this was a creative project we submitted almost 20 years ago. And then I was plugging it into PowerPoint. Okay, so back then, you could just download all these sound effects today, but back then, we didn't have that option. So I had a cat at the time, so I decided to get the sound effects out of my cat. Now, my cat was Maine Coon. The Maine Coons are kind of like dogs in a lot of ways. So she liked being roughhoused. She enjoyed roughhousing. And so I just grabbed her and started squeezing her. And then she was purring. She thought that we were playing. And then I'm thinking, this is not what I want. So I kept squeezing and squeezing and squeezing. And then eventually she started to cry. I'm thinking, this is just right. So let me squeeze it a little bit harder. And then she just went ballistic. I got scratched pretty bad, but I got what I was looking for. All right. So from that height, you're thinking splat. In reality, the reason why I picked a cat is because there are 2 possibilities when it comes to cats. One possibility is the obvious, the splat. Out of 2 possibilities, splat or survive. I got news for you guys. Cats will be fine. This is called a mind twister. You'll have plenty of these. Okay, one of the things that I want you to remember, I want you to know and remember, I'm not your friend. I'll set you up for failure. All right? I'll teach you the facts, and I'll make sure that you understand the concepts. And the only way I know that you get the concepts is through these mind twisters. A lot of these tasks, especially the conceptual portion of the test, are really, really tough to do because I'm looking for details which are usually not there. I set you guys up. Everything that we discussed so far is boom, boom, boom. You're hitting concrete. It's not survivable, blah, blah, blah. And all of a sudden, a cat does it, and the cat will be fine. In fact, the longer the distance that fall is, the better the cats will do. Anything over 70 feet, no problem for a cat. Anything under 70 feet, still maybe survivable. Injuries tend to be a lot more severe. So the question is, how would I know that?
I'm here to demonstrate how
this phenomenon has a name. It's called the high-rise syndrome.
Whiskas' new savory nuggets with crispy outsides and soft centers compare to the typical dry cat food. Observe the difference at impact. Now ours. Trying this again. These cats are totally ruining the experiment.
It's called high-rise syndrome because it happens to cats living in high rises. A lot of cats end up falling from buildings chasing cat food. When we talk about cat food, I don't mean dry cat food. I'm talking about things that the cats may find interesting, like the birds flying around. And if the cat is on a balcony, if there's a bird nearby, the cat is going to chase it. If the cat is on a windowsill, once again, if there's a bird, okay, they will once again go after it.
A very different rescue
Or the worst case
was undertaken across the country atop a burning building in Los Angeles, California. A tabby cat had found herself trapped on the roof of a single-family two-story home. As flames consumed the building, the anxious family members waited for news of their loved ones trapped inside. A brave fireman made his way to the first-floor roof. The frightened cat looked on as her rescuer approached. The fireman needed to get inside to search for human occupants, but he wasn't going to neglect the poor cat who was too frightened to move. Quickly, the fireman grabbed the animal under her chest.
Okay, so you know what he's about to do, right? He's about to toss the cat away. Okay, so would he do that with elderly? No, somebody's child? Absolutely not. Baby? No way. Dog? More than likely, no. But with a cat, he's about to toss the cat away. And most of you guys are not cat lovers. If you were to see a cat, probably would speed up if you see a cat on the road, you would probably speed up, not miss out on the opportunity. And you're thinking, yeah, this guy's probably the same. He's being a professional in a sense that he's getting paid to do the job, but obviously he's not very happy about it. Now look at the way he's going to toss it. And he's tossing the cat. Not only is he tossing the cat, but also he's spinning the cat. Oh wait, you're thinking, oh, obviously the guy doesn't like the cat from the intensity. But you got to look at it from a different perspective. Guys, this is 20 years ago. If the building is on fire, people would just come on with these camcorders. All right, so we'll get a different perspective on what's going on.
The burning flames.
This guy is actually passing the cat onto this guy. And this guy is looking up. The cat flying towards him. He's just acting on
natural agility.
Look at the landing. It's beautiful.
The lucky cat.
And then the cat
was able to land and race away.
Runs into the burning building.
All thanks to the brave act of one hero.
This you can do with a cat. It's just fine. The cat is going to be up to the land. The cats can survive something.
Brave fireman.
Now, there are two reasons for it. Number one reason is because cats got extra muscles in their hind legs as well as the shoulders. They got 3 extra muscles. They can absorb the impact so much better, which means that they're able to increase the impact time so much more than we can. All right? That's the secondary reason. So the question is, why is it that they end up doing better in the longer distance falls than the shorter distance falls? So that's something that we will have to study later on. So they got extra muscles in their hind legs as well as their shoulders. They're able to increase the impact. They're able to increase the impact time, which means that their bodies are capable of absorbing impact so much better than we can. Increasing the impact time means that they're able to reduce the acceleration to survivable levels. So here's the airplane, bucket passengers inside. It gets slammed against the ceiling. So the question is why? And you guys came up with a bunch of answers, so we'll investigate. So I decided to contrast that to this guy inside the elevator. He was on the 10th floor. He's got a broken neck. My question was, why did he break his neck? And you guys came up with theories. In physics, with theoretical physicists are the ones who come up with theories. Has to pass the theory review, and then you do the experiment. Based on the majority view, and this is the most commonsensical view that you could come up with, this would be the storyboard if you were the artist. So the cable snaps, tongue is sticking out, the speed is going up. It's going to hit the ceiling. What goes up must come down. The first or the second impact is going to break his neck. That's it. All right, so this is what you will come up with. So now that we have a theory, so the next step is test the theory. How do you test the theory? There are people who do this for you. Those are experimental physicists. So those are the guys who will do the experiment. All right, so there's an easy way to test this theory. Obviously, I'll find you guys in an elevator, a cable, and then you'll find out exactly what happens inside the elevator. Except, obviously, it's illegal, so we can't do that. So normally, we would do an experiment for something like this, an animal experiment. All right. Let's just run a simple demonstration that we get a condition. I don't know. All right, stop this. All right, so let's take a look. All right, so we got this little elevator, and then we'll do a simple experiment. All right, so I got this toy. Shit. All right, so what I'm gonna do is I'm gonna drop this, and then we'll check to see if it's gonna go to the top. I'm gonna drop it from this side. We'll check to see if this thing is gonna go all the way to the top. Or maybe use a ball. It's easier to see. Okay, so when I drop it, we'll check to see if it goes to the all the way to the top. All right, ready? All right. When I drop this, how many of you guys think that the ball is gonna go to the top? Hopefully you guys aren't that gullible at this point. All right, so here's what I did. I talked to an expert in the field. This guy has a PhD in quantum gravitational field theory. He said, Ken, the ball will never go to the top of the elevator set. Instead, the ball is going to go to the middle of the elevator. All right, the middle of the elevator is the center of gravity. The center of geometry is the center of gravity. So which means that the ball is going to get pulled to the center, and it's going to become suspended right at the center here somewhere. Got it? That's what it is. So when I do the experiment, watch the ball just rise up to the middle, and then unfortunately that's not going to happen because I end up breaking this shit. All right, this is not. All right. Okay, so instead of the ball, I'm going to use something slightly lighter. All right, so this is not going to work. Okay, so it's going to go to the middle of it. All right, so let's turn it sideways. We can still do the experiment. All right, so you should see it actually rise to the middle. All right, ready? So I'm going to do it. I want you guys to watch it carefully. Does it go to the middle? Yes or no? Does it go to the middle? Yes or no? So when I do the experiment like that, you will notice that you're not able to see anything because things usually happen real too fast. So instead, what I'm going to do is I'm going to repeat the same experiment using keys. If the keys rise up, you're going to be able to hear this. Okay, you're not going to be able to see much of anything. Number one, we're getting a lot of reflection. Number two, things are happening way too fast. All right, so when I do the experiment, will the keys rise up? Okay, so just listen for the sound. Notice that you don't hear anything, much of anything, right? So which means that the keys don't really rise up. What that means is the keys will remain on the floor. And they're going to be falling at the same rate as the elevator does. So the conclusion is the person inside the elevator does not leave the floor, remains on the floor at all times. So the question is why? That question has something to do with the sky. Remember Galileo said everything's going to fall at the same rate? Like if you drop two objects, one heavy, one light, hammer and a feather.
And I'll drop the two up here, and hopefully they'll hit the ground at the same time.
Which they do. So a hammer and a feather end up dropping at the same time. And that's true in the absence of air friction, guys. With the air friction in effect, these keys and this piece of paper are not falling at the same rate. So how do you explain the fact that the person inside the elevator is falling at the same rate as the piece of paper? All right, so put the keys in, put the piece of paper on top, and then just drop it. Notice that shielded from the effects of air friction, everything is still falling at the same rate. All right, so that's what Galileo meant. He said shielded from the effects of air friction, everything is going to fall at the same rate, in essence, inside an elevator, in this case. All right, so elevator is relatively heavy. So the effects of air friction on the elevator is unnoticeably small or ignorable. The person inside the elevator is shielded from the effects of air friction, so it's going to be falling at the same rate as the elevator will. All right, so that's what it is. But we got a slight problem. The problem is we've got a person inside, despite the safety system, has got a broken neck. So the question is it remotely possible for this scenario to be accurate? Or is it something that I end up pulling out of my butt? I got news for you guys. This scenario is completely made up. I knew one day it might happen. And when it did, I was lucky enough to catch it on TV.
Their elevator plunged 40 stories. That story tops tonight's news briefs. Miraculously, the women suffered only minor injuries. One woman broke her ankle, the other broke her leg. After traveling down 6 floors, the elevator suddenly broke loose and began its free fall descent. Authorities are investigating the cause of that accident in New York.
All right, so the question is, how did this person break his neck? Get back to that question.